In our last video, we took a look at monotonic sequences. Let's look at these examples that we know to be monotone and what is true when they are convergent, about their convergence and boundedness. So let's look at just the ones that we said, yes, they are monotone. So this said, yes, it's monotone. It was convergent and it was also bounded. This one we said, yes, it was monotone. It was convergent. It was also bounded. Down here we said, yes, it was monotone, but it was not convergent, nor was it bounded. Yes, it was monotone. Yes, convergent. Yes, bounded. Yes, it was monotone. No, it was convergent. And no, it was not bounded. And so a pattern we might see emerging here is that whenever it was a monotone sequence, the convergence and the boundedness, they always had the same answer, right? So either they were both bounded and convergent when they were monotone, or they were neither one bounded nor convergent when they are monotone. Turns out that that is true. So we have this monotone convergence theorem. It says a monotone sequence is convergent if and only if it is bounded. So if we have a sequence that we know to be monotone, it turns out that its convergence and its boundedness are going to have kind of the same answer. And so in that forward direction, if we wanted to prove this in the forward direction, if it is convergent, then it's bounded. Turns out this is true. We've actually already proven this. We proved this back in the section 4.1 videos. Section 4.1, or theorem 4.1.13 says if a sequence is convergent, then it is bounded, right? Or every convergent sequence is bounded. Right, so that's an easy way to go through the forward direction. Actually, maybe I should not put that box yet. Let's wait till we're done with the whole proof. Right, so the reverse direction, we want to assume that it's bounded and then show that it must be monotone. Right, so let's suppose that our sequence is a bounded increasing sequence. So if we have a bounded increasing sequence, let's let S be equal to the set of these terms in the sequence. So this is bounded and non-empty, no-nempty. So it's bounded and non-empty. So what do we know about this set? Well, we have a set that's bounded and non-empty. So by the completeness axiom, this set S has a supremum. Right, so our set has a supremum. So let's say that the supremum is equal to S. And so our claim is that our sequence is going to converge to that value. So I claim that the sequence converges to S. So given epsilon greater than 0, we have S minus epsilon is not an upper bound. For S. So if it's not an upper bound for S, there exists a natural number n such that there is a term associated with this that must be greater than S minus epsilon. Since we have an increasing sequence and S is an upper bound, since we have an increasing sequence and S is an upper bound for S, we have S minus epsilon should be less than S sub n, which should be less than or equal to S sub little n for all n greater than or equal to n. Hence, S minus S sub n is less than epsilon for all n greater than or equal to n. And we have that the sequence converges to S. If that sequence S sub n, if our sequence S sub n is decreasing instead, use a similar argument with an infimum. And that would prove it, right? So it turns out that whenever you have a monotone sequence, every single monotone sequence is convergent if and only if it is bounded. So if you have a monotone sequence and you can say it's bounded, then you know it's convergent. Or if you have a monotone sequence and it's convergent, then you know that it's bounded. Notice, though, if we have a sequence that is both convergent and bounded, that does not necessarily imply that it is monotone. So there are examples of that, where we have convergent bounded sequences that are not monotone. The alternating harmonic series would be an example of a convergent bounded sequence that is not monotone. All right, we will look at Cauchy sequences in the next video. I'll talk to you guys later.